The next step is let's take everything we've seen, everything we learned, to generate our word usage classifier. So let's consider what we're going to do here in our model. Let's build out the workflow. So here comes our text. We want to count it, right, to the bag of words. Let's go ahead and use a TF-IDF vectorizer. That step there. And what comes out here will be fed to a machine learning model to make predictions. Although at this step, well, actually in this step here, we should include bigrams. We'll go ahead and also include stop words, or use stop words. Let's also apply lemmatization. In other words, we want to reduce each word to its dictionary form. This will ensure words like run and runs are going to be counted as simply as run. And of course, we'll use pipelines to encapsulate the entire process as one estimator. Let's go back here. Okay. Let's go with our task. So let's get our documents. So we're going to include the census for the animals and census for Python, the language. For these documents, and in order to use them for supervised machine learning, we have to have labels for each of our documents. So in this case, we'll go ahead and create a list of either a string animal or the string language. Okay, with our stop words, let's go ahead and create a string of our stop words because we want to create a lemma of our stop words. Remember, since we're going to apply lemmatization, the stop words that we provide need to be lemmas. That isn't the case initially. So we're going to iterate through our process stop words and return the lemma and return it as a set. When we use the stop words keyword argument in scikit-learn, we need to provide the stop words as a set. That's the data structure we provided. So we get back a set. Here's our pipeline. Okay, use stop words. We're going to go ahead and use lemmatization. So we're going to use that lemmatizer we defined up above. And we're going to both count words and bigrams. So our tokens are both words and bigrams. So now comes the point of what machine learning model should we use. And notice for this lecture, there was not an emphasis about what machine learning model to use for natural language processing. We're more concerned about the upstream part of our workflow. What do we need to do to get our data, our raw data, into a format for our downstream machine learning model to learn from? All the processing, all the steps involved, all the things we need to consider to boost the signal, reduce the noise of our data set. That's the point of this lecture. So now let's choose a machine learning model to do the predictions. In this case, we're going to use the naive Bayes model. So this is a probabilistic classifier that's going to calculate conditional probabilities using Bayes' theorem. And the term naive is applied because it assumes that the features are conditionally independent from each other, which is a naive assumption, but it's going to help us to generate a tractable model, a model that we can easily train. And naive Bayes is a very popular model to be used for natural language processing because it's quick to train, it scales up nicely, and can be used as a baseline model. In other words, let's go ahead and get a model that works, that works decently, and then we can go ahead and worry about a more complicated model later on. And we go and compare how well the complicated model works compared to this baseline naive Bayes model. Let's talk a little more about naive Bayes. So it's going to work by determining what class should a document be assigned based upon the frequency of words in the different classes in the training data. For example, what the naive Bayes model is going to do, it's going to pick up patterns like the word tail, let's say tail, or fang, let's say fang, appears more often in documents referring to Python the animal as opposed to Python the programming language. It's going to use those probabilities, use those observations to train the model, and that's how it's going to make classifications. Okay, So let's go ahead and use our naive Bayes model. So that's where it is, multinomial Bayes model. Let's create the pipeline. Let's fit the pipeline with documents labels. And let's look at the training accuracy. All right, and see how quickly we can do this. The nice thing about pipelines, because I can always easily switch out the predictor we use. All right, so the training accuracy is 97%, or close to 98%. This is pretty high. What are some things I should consider at the moment? What should I go ahead and do? What should prevent me from celebrating right now that I have a model that has a high training accuracy? Well, it's just the error metric or the performance metric for the training set, right? Let's see how well it does on a test set. So what I'm going to do here, I'm going to go ahead and just create various test documents. Test documents, we can see how well the model performs. So I made these up, and I kind of paired them. I did my best job to pair them. So one example is my Python program is only 100 bytes long. So we understand that's Python, the programming language. The next one says a Python's bite is not venomous, but still hurts. I can't find the error in the Python code. Where's my pet Python? I can't find her, and so forth. Notice I like to do some clever things here. Let's see how it treats the word loop. Maybe that will confuse it. So I use for and while loops for when writing Python. And then for the next one, I say the Python will loop and wrap itself onto me. This is going to be an interesting test case here. I use snake case for naming my variables. So we understand here that this is Python, the programming language. But let's see if our model gets tripped up if we use the word snake. To go ahead and play around with that, see the different sentences we constructed. Some of these are pretty interesting. In other words, it's not. Some of these might be some curveballs for our model. The naive Bayes model is a probabilistic classifier. So not only can we predict what class it's going to assign the observation, but we can also return a probability. It's confidence that this observation is in this class. So we'll go ahead and predict the probabilities. We'll go ahead and use a threshold of 50% when saying which class this observation belongs in. We're going to iterate through our sentences, and for each sentence, let's see what it predicts, what the true answer was, and what's the probability for being in that class. So see how correct it got, how correct it was. So my Python programming language is only 100 bytes long. And it set the language, good. And it's 74%, so that's pretty good, pretty good. All right, the Python's bite is not venomous, but still hurts. Ooh, that one it failed. It failed, and it was pretty confident in this case. It said it should be 71% chance at beating the language, but that is not the case. I can't find the error in the Python code. Okay, that one also got correct, 72. Where's my pet Python? I can't find her. Oh, that one also failed. Failed, but notice now here it says it's 53%. So it failed, but it's better than failing at saying it's 75% confident that it's Python, the programming language. All right, use for and while loops. Okay, pretty high confidence, pretty high probability. So it's probably looking at things like loops and while and for probably appear very often. Very important features in our analysis. These features are very discriminative. Okay, the Python will loop and wrap itself onto me. Looks like I did a poor job there, 66% for the language. A snake case, oh, that one was pretty impressive, right? I would thought if it looked at the word snake, it would think it's Python, the animal. But I'm guessing here is that variables is a very important feature. Variables probably appears very often in documents referring to Python, the programming language. And yes, the probability isn't so high, but it was enough to predict this observation to be Python, the programming language. Okay, this one it scored correctly. Not very high, but it scored it correctly. It figured out it was the animal. Virtual environments to manage package versions. The language, pretty high probability. Perhaps virtual and packages and versions. Those are words that I would argue, appear very often in Python, the programming language. The largest snakes in the environment, that was the animal. So that got it. That was correct there. So you can play around with this. You try different sentences, see if you can trip it up. But I think our classifier does a decent job.